As you know, my name is Anthony Love, and I am the Research Operations Manager for the Department of Geological and Environmental Sciences at Appalachian State University. This is a liberal arts school located in the Southern Appalachian Mountains of Boone, North Carolina. So my main focus within geology is the identification and classification of unknown meteorite samples, primarily that come from the desert regions of Northwest Africa. And tonight, I was going to talk a little bit about the potential opportunities for using deep learning techniques to analyze and process X-ray maps that are made of shergotite meteorites. So as kind of a roadmap to show you what we'll be talking about tonight, I was going to give a brief overview of what shergotite meteorites are. Hopefully, some of you are familiar with these types of rocks. Talk a little bit about what they are and why it is geologists are interested in studying them. I am going to give, admittedly, probably more of a 2-cent tour of X-ray interactions with samples, X-ray mapping, and the types of instruments we use to collect X-ray data, as well as the samples that we use to analyze. I'll be discussing what we can see examining different X-ray maps and how these maps can be used to identify mineral species and possibly estimate the abundance of these minerals occurring within rocks. I'm going to conclude by talking about some of the limitations and challenges we have in using this technique, but hopefully I want to turn it around and be positive and talk about the opportunities that I believe could be utilized by deep learning processing to enhance our understanding of these samples. So shergotites are a variety of Martian meteorite. These are basaltic rocks, and basalts are a type of extrusive igneous rock for those who are not familiar with geology. Those are rocks that crystallize from magmas and lavas, either beneath the surface or at the surface. Typically, the minerals within the rock represent the composition of the liquid that they've formed from. And in the case of basaltic rocks, they're typically enriched in heavier elements like iron and magnesium. We recognize we have samples of Martian rocks in our collection because they're distinct from many other types of meteorites. One of the first pieces of evidence we have to make this distinction is based on the age at which these rocks crystallized. Now, most of the meteorites we have in our collections here on Earth crystallized or formed around the same time, 4.56 billion years ago. And now, in comparison, most of the meteorite samples that we can age date crystallized at a much younger time, sometime between 120 million years and 1.2 billion years. And I know those ages sound old, but again, comparison to the vast majority of meteorite samples, these are relatively young rocks. Shergotites also contain unique chemical signatures that we find in the minerals olivine and pyroxene. Now, these minerals are very common to most meteorite types that are made out of rocky minerals, but the shergotites contain more iron-rich varieties of these olivine and pyroxene minerals. And specifically, they have a very unique ratio of the elements iron and manganese. We can also measure the signature of oxygen isotopes. It serves as another way to chemically fingerprint them. And we see that they have a consistent ratio of both heavy and light isotopes of oxygen. And typically, rocks that show a consistent ratio are surmised to be to originate from a single parent body. Now, the final piece of evidence that was kind of a clincher for geologists that originally inferred these rocks came from Mars is the Viking spacecraft landed on the surface of Mars in 1976 and took a sniff, so to speak, of the atmosphere and was able to determine the composition of the atmosphere at the surface. Later in 1983, scientists studying a meteorite that was collected from Antarctica drilled into a melt glass formed by impact and measured almost the same chemical signature of the Martian atmosphere. Oops. Let's see. So geologists are most interested in petrogenesis. That is how rocks form or originate and what types of geologic processes are responsible for changing these rocks. Now, shergottites are considered to be pristine samples of igneous rocks. We make that comparison based on looking at other types of basaltic rocks that come from asteroids and bodies like the moon. In these other cases of rocks, in these other cases of other bodies, these rocks show the effects of metamorphism through heating. That is, their chemical signatures have been altered. And we can also see the activity of aqueous fluids that have altered some of the original compositions. A lot of the shergottite meteorites do not show these same effects and hence record the original chemical signatures of the minerals when they crystallize. Now, for a geologist, a basalt is a really important rock to understand how minerals crystallize from a magma, because we can learn about the sequence of crystallization based on the chemistry of the minerals within the rock. We can understand more about the conditions where these rocks are crystallizing, such as the temperature at which the first minerals form, the pressure under which these minerals are crystallizing, and the oxidation state in the magma where they're crystallizing. Finally, we can understand information about the cooling rate, which gives us an idea about where these rocks are crystallizing, whether it be in the shallow surface of the crust or at the surface. Now, basaltic igneous rocks also tell us about the nature of their source magmas. And for geologists, this is really important because we recognize magmas form either in the subsurface below the crust or within the mantle. And so they can give us a good proxy of the chemical composition of the mantle of the body. Now, of course, these meteorites do not represent the entire chemical recipe of Mars because we're only sampling volcanic rocks that are present in a handful of locations on the planet. That's why it's really important to have missions like the Mars 2020 mission, where we've sent a rover across the surface that's collecting samples that will hopefully be returned to Earth to give us a better idea of the geologic diversity in different types of rock deposits that occur in and around the Jezero crater. Now, finally, we can use basalts to learn about the nature of magmatic processes. We know a lot about the nature of magmatic processing here on Earth from our studies of terrestrial igneous rocks, but having other samples that can tell us about this nature allows us to compare between different planets and learn something about magmatic processing as it occurs in different bodies and on bodies in our solar system. Now, typically when we analyze these samples, we can use a variety of different types of microscopes. The image on the left shows image from a cross-polarized light microscope. That is a type of microscope that's used to observe how light is refracted off minerals. What we can see is the colors of different minerals, which in this case, these brightly colored grains are the mineral olivine. And then we can see these gray grains that are the mineral pigeonite, a type of pyroxene. These are silicates that commonly make up different types of basalts. And we can also see the arrangement of the minerals within the sample, but we can't understand anything about the chemical composition at this point. The image at the right, on the right, is what's known as a backscattered electron image, and this comes, in this case, from an electron microprobe. What we're seeing is the grayscale hues of color show us that there's the average atomic weight of different elements that make up a given compound. So for instance, the very bright spots in the image correspond to mineral grains that have a high average atomic weight, or they're composed of heavier elements. So in this case, these grains are likely composed of iron-rich minerals like oxide minerals or sulfides. In the case of the darker spots, like this one here, these areas are composed of minerals that contain an average atomic weight that is lower. And so we're looking at minerals with lighter elements. In this case, the mineral plagioclase feldspar. Now, in these two images, we're looking at more or less the same area. This crystal here with this kind of teardrop shape is this same crystal. So we can see the difference between what the images show us. Now, here within the electron microprobe image, we're starting to see some of that chemical nature coming out. But the X-ray mapping techniques that we use and the processing of X-ray data gives us a much stronger sense of how elements are distributed within minerals within a sample. So one of the really important reasons we utilize this technique is that it's a non-destructive way to identify minerals, and we can identify these minerals in situ as they're within a sample. So in other words, we don't have to crush up a sample and dissolve it using chemical means. We can see it in the context of the other minerals within the rock. This allows us to determine a modal abundance, or the volumetric abundance, through estimation of how much of each mineral occurs within a rock. Now, if we can identify the minerals and identify their abundance, we can also use the texture or the arrangement and distribution of the minerals that allows us to make interpretations of how it formed, but also leads us to information about what type of rock it is. That's really important for a geologist studying meteorites, because oftentimes meteorites represent disparate rocks from unknown bodies. We have an individual rock sample, and we have to use the information about the minerals and their textures to assert something about how these rocks form. One of the other really important uses of these X-ray maps is they serve as a reconnaissance tool for further studies. They show us either anomalous features within a sample or previously unseen minerals due to their size that allow us to better understand how samples like this form. So here's where you get really the 2-cent tour of X-rays and X-ray mapping. When we're mapping a sample, we're trying to measure the characteristic X-rays that relate to the elemental composition at a point where that beam is interacting with the sample. So we use electron beam instruments that can shoot a high energy beam of electrons at a point. And during that interaction, we can see here on this cartoon on the left, we have an incident X-ray beam coming in from the electron gun of the electron instrument, and it can knock out an inner shell electron from its orbital. And we can see that happening here. As a consequence, that atom is now unstable, and this atom, of course, represents a specific element. Because this atom wants to remain stable and not ionized, an electron from the next outer shell will fall back into that inner shell orbital. And in doing so, it gives off a characteristic X-ray. And we call them characteristic X-rays because the energy that's released through that X-ray is characteristic of specific elements. And we can see that here down on this graph. When we're measuring the signature of these X-rays, we get a measure of the intensity of the number of X-rays counted, as well as the specific energy level. And typically the energy level that we're most interested in for characterizing a given element in a mineral is this K alpha X-ray. So you can see here on this map on the right, we're actually looking at the calcium K alpha X-ray map of this area of a sample. So these X-rays are generated as a function of the position of the beam. So when we're creating a map, we're actually rastering the beam across an area. And what we produce is a distribution of the elemental composition at any point that's the given result is part of the mineral composition. In this map, what we see is there are dark areas where we're not measuring calcium X-ray signature. And then we see, according to the scale, there are very intense areas like these lines and points that are red, where we measure higher intensities of X-rays or higher counts of X-rays. So in this map, we have areas where there's virtually no calcium, and then we have some regions where there's very high calcium and regions where we get more intermediate levels or concentrations of the calcium. These concentrations correspond specifically to the chemistry of different types of minerals within the sample. So essentially what it shows us is we can create a map of minerals based on their chemical concentrations. One of the main advantages to this technique is also it has a high spatial resolution. We can measure a given element down to concentrations of less than half a weight percent to 1 weight percent at a resolution of about 0.33 microns per pixel. I know some of you are familiar with the measurement of micrometers. Does anybody else know what micrometer corresponds to, how it correlates to a millimeter? It's all right if you don't want to speak up, but there are 1,000 micrometers in 1 millimeter. So we get very high resolution at a very small scale. So some of the instruments that we use to produce this X-ray signal, as I said, are electron beam instruments, one of which is a scanning electron microscope. And this is the microscope here. This is the electron column. And this is what physically creates the electron beam that then interacts with the specimen in the chamber in here. This instrument here on the right is called an energy dispersive spectrometer, and it's capable of measuring multiple energies representative of different elements simultaneously. It can do a really good job creating maps very quickly, and it produces a very high intensity X-ray signal. Now, typically, we use scanning electron microscopes to qualitatively identify minerals, but in some cases where we use standards of known compositions, we can use it to quantitatively analyze the composition of minerals. If we're looking for more precision, high precision chemical analyses, we use this instrument called an electron microprobe, also known as EPMA. This instrument uses a different type of detector called a wavelength dispersive spectrometer. And on this particular model, I believe there are 5 spectrometers. One of the main differences in this technique is we're measuring how the wavelength of X-rays is dispersed or reflected across the face of a crystal in one of these spectrometers. So one of the primary differences is an individual spectrometer is measuring a single element within a mineral at a time. And we can change the position of the crystal to gather information on other elements, but really within a single spectrometer, we're only measuring one element at a time. The advantage this gives is that it gives a much higher resolution spectra of what the elemental composition of a given mineral is. So we can determine with much greater precision the chemical composition of a small area within a mineral, and we can analyze up to 5 different elements at the same time, and then we can change positions of the spectrometers to gain information on other elements. One of the minor disadvantages is this technique is a bit slower, but what the increase in precision is worthwhile for how much more time it takes. So typically the samples that we're working on are actually slices of rock that are cut from the meteorite and then ground until they're 30 microns thick, or 1/300th of 1 millimeter thick. We glue these slices to glass slides, and they're called thin sections. These are images of different types of shergottites that we're examining using plain light or unpolarized light. And you can already see that there are distinctive differences, not only between the colors of mineral grains, but the size of mineral grains, as well as the distribution of different mineral grains. An additional aspect of this type of analysis is it allows us to see more macroscopic features, such as geologic processes that affected the rocks after they formed. In this case, on this sample on the left, the poikilotic shergottite, we're looking at a shock vein that cross-cuts it. And this shock vein is representative of the hypervelocity impact processes that affect and liberate these rocks from the surface of Mars. So these are the types of samples that we can analyze, and even with them being thin, we are minimizing the volume of the mineral that's analyzed using the electron beam techniques. Now, so these X-ray maps are really good at creating a picture of the elemental composition of minerals in a space that's representative of the rock. So if we can understand what minerals contain what elements, we can also get a sense of what the overall rock texture is, which gives us inferences into how it formed. So here we're looking at X-ray map of the element magnesium, and we can see these bright grains are the mineral olivine, one of those magnesium iron silicates. We've got the dark areas which don't have any magnesium. That's likely the mineral plagioclase feldspar. And then we've got the areas of intermediate brightness that are the different varieties of pyroxene minerals. Now, in this image on the bottom right, this is a false colored image of the same area. And the addition of color allows at least the human eye a better chance at picking out minerals that are more dim in this grayscale image of the element map. So it gives us a sense where we see these blue minerals those are much dimmer in the dark areas and thus hard for the human eye to pick out. This might be another aspect where the computer that can measure pixel brightness values will have a much easier time identifying these elements and hence minerals. So because we're interested in the minerals in the rock, we want to know something about what those minerals can tell us about how an igneous rock like a shergotite crystallizes. In these maps, we're looking at false colored X-ray maps, in this case, of the major element, magnesium. And we call it a major element because it's one of the elements in high enough abundance that it actually occurs in the mineral formula or chemical formula. Major elements constitute between 100 to down to 1 weight percent of a given part of a mineral. We also can measure minor elements, those that occur in concentrations between 1 and, let's say, 0.1 weight percent. What we can see from the map of magnesium concentrations is that there's variation in the amount of magnesium between the center of the crystal, where it's more magnesium rich, and the outer rim of the crystal, where it appears to be more magnesium poor. We can also, of course, see other minerals that are very magnesium poor. But when we look at minor elements such as calcium, we see that calcium is relatively evenly distributed within the crystal of olivine. We can see a bright spot here and a little bit brighter spot here, but those correspond to inclusions within the mineral. Here we have a map of the element chromium and one of the minor element phosphorus. And these show this interesting detail of these concentric rings. These are very similar to the growth rings that we see in a tree, and they record how the crystal is growing in this liquid. Now, for geologists, that's really important because we can ask the question about the liquid and about the rock, that can we determine whether the olivine crystals were present before the rock crystallized, i.e., were they added, or did these minerals crystallize in place? And this is very important for us to understand this relationship, to understand the overall chemical composition of the magma. Because if we're looking at a rock where the crystals grew in place, the overall chemical composition of all the minerals within the rock is actually representative of the overall chemical composition of the magma. If these minerals were added or crystallized before that magma or liquid interacted with them, then the liquid that crystallized the rest of the rock is not representative of this composition. This is a detail that perplexes geologists, but it is an important detail of understanding whether the chemical composition, what the chemical composition of magmas on Mars is. In this case, let's see, I think that's what I needed to say about that. So in these images, we're looking at the image on the left is what's known as an electron, a backscattered electron image. And it does a really good job of showing us what the constituent minerals of the rock are and how they're different from one another according to their average atomic weight. Now in the image on the right, this is what's called a false color composite X-ray map. And it's composed of 3 different images that are stacked, and each image corresponds to an elemental composition. In this case, a map showing calcium represented by the red shades, iron represented by blue, and magnesium represented by green. And we actually see a lot more detail in the case of some elements that, or some minerals that were not obvious in the map on the left, we can see these bright red crystals of a mineral called marlite. We can also see that there's a lot more distinction and diversity in the composition of these green and yellow elongate minerals, which are pyroxenes. So this is an example of why these X-ray maps are so useful in visualizing and understanding the different types of minerals and the elements that make them up. Now, it's really important when we're performing these analyses and making these maps that we understand something about the minerals that we expect to find within the rock. That allows us to choose a suite of elements that's representative of most of the minerals that we expect to find in the rock. Now, we can make these element maps for any number of different elements, I believe currently from the spectrum as light of elements as lithium to as heavy of elements as uranium. But we really ideally want to choose elements that are in measurable abundances, but also reflective of the overall chemical composition of a number of the species. So in shergottites, there are typically silicate minerals like pyroxenes, shown here as these two different varieties. We have another calcium aluminum silicate mineral called feldspar. And then we also find oxide minerals like these iron titanium oxide minerals, ilmenite and titanomagnetite, as well as a sulfide. And then we find finally this calcium phosphate mineral known as marlite. Now we want to, since we don't all speak chemical formulas, we need a way that allows us to distinguish what the different minerals are making up crystals within the sample. So I have this chart of chemical compositions measured from this sample, which is known as a basaltic shergottite. In the top row, we have the names of constituent minerals within the sample. And then on the first column, we have the elemental composition that we measure when measuring these samples. We can see that these elements are bonded with oxygen because most of the minerals that we're analyzing in this case all have oxygen bonded to their crystal structure. So if we look at the first type of mineral that makes up a major component of a rock like this, we're talking about the pyroxenes. Now, if you remember, there's two types of pyroxenes in these rocks, and we can distinguish them based on their calcium concentration. So the mineral pigeonite has lower concentrations of the element calcium oxide, and augite has higher calcium. We also see that these two minerals are enriched in the elements iron and magnesium. And so if we look over here at these different maps showing magnesium, iron, and calcium, we can see that the pyroxenes stick out like sore thumbs based on their magnesium and iron concentrations. We can look at the calcium map to help us distinguish which variety of pyroxene we're looking at, whether it be pigeonite or augite, based on the grayscale. We can see that the pigeonite forms the insides of some of these grains with these darker areas of gray pixels. And then the augite forms that much brighter rim around these crystals. When we see variation in chemical composition, one of the things it tells us is how the mineral is growing from molten liquid like a magma or a lava. It also tells us that the mineral is growing relatively quickly and that the composition of the liquid that it's growing from is actually changing. We call these zoned crystals. Now, we also have another major mineral in this rock called plagioclase feldspar, and we can see that it's distinct from the two types of pyroxenes based on the fact that it really doesn't have any iron or magnesium to speak of. It does have some calcium. So again, we can use that calcium map and the brightness values of the pixels in areas like this to determine that those are areas composed of plagioclase feldspar. We can kind of cross-reference it between the other maps to see that a lot of those same areas appear as dark areas where we're not measuring any concentrations of magnesium or iron. In the calcium map, we also have these much brighter areas of pixels that demonstrate there's much higher concentrations of the mineral marlite, which is a calcium phosphate. And we can see that the abundance of calcium is much higher in these regions of these maps. So it makes the marlite stick out like a sore thumb. Now we can also use maps like the iron map to determine which grains might be some of those lesser abundant iron oxide minerals, as well as the iron sulfide minerals. Now, in this chart, we don't have a chemical analysis for the iron sulfide mineral because it doesn't contain any oxygen. So it's a difficult comparison to show. But what I can tell you is the abundance of iron is relatively similar to the abundance of minerals like ilmenite and titanomagnetite. So the brightness is not going to be dramatically different between those three different mineral phases. We can assert that those mineral phases make up a lower concentration or abundance mineral within the rock. So it's not a major rock forming element. So in this case, we've actually collected a map showing the concentration of aluminum in the different minerals within the sample. And then again, in this case, the main aluminum-rich minerals are the plagioclase feldspar that occurs as a major component of the rock, and this component, a phase that we call mesostasis. Mesostasis is essentially in a fine-grained intergrowth of the last minerals that crystallize within the rock, right as the last bit of liquid that crystallizes minerals has cooled. Now we can see the distinction based on concentration between the plagioclase feldspar, and in this case, the mesostasis, the plagioclase is composed of much brighter pixels, whereas the mesostasis typically occurs in contact with the plagioclase as these areas of darker pixels. So one of the other areas that's really important in understanding the composition of these rocks is understanding the volumetric abundance of minerals in a given sample. And I think this is one of the areas where deep learning techniques might really provide significant aid to making this assessment. What we're doing here is taking the three different component maps that make this composite image and basically measuring the area abundance of certain pixel brightness values. So in the case of calcium, we can look at we can estimate the abundance based on area of the mineral marlite, that very calcium-rich mineral. We can also estimate the abundance of that plagioclase mineral feldspar, that plagioclase feldspar mineral, again, based on the brightness values of pixels for plagioclase. Now, with respect to the pyroxene minerals, we can use either the magnesium or the iron map to measure these values in this case, because it appears that those grains have relatively homogeneous concentrations of these elements. We can also measure them independently and use that as a cross-reference between the different values that we get for those minerals. And again, we can use maps like the iron map to determine the abundance of oxides and sulfide minerals that occur within the sample. This technique is a way that we can measure when we measure the abundance of different mineral species within a given area and hence estimate the volumetric abundance, if we correlate the chemical compositions that we measure with an electron microprobe with the abundance of the minerals within them, we can get a measurement termed bulk composition that talks about how much element each mineral within the rock contributes to the overall chemical composition. Now, in Dr. Huang's lab, we have an instrument called a mass spectrometer that gives us a much higher precision method to do that by measuring trace elements that occur in concentrations down to parts per billion. But this gives us a good first round assessment of what that bulk composition is of a sample. So one of the obvious challenges that we have in interpreting these maps is there's experience that's involved in the observations. In this case, we're looking at a map created of a type of rock called a breccia. This is a rock that's composed of broken up fragments of pre-existing rocks. And in this case, we're looking at a map showing the elements of phosphorus, magnesium, and aluminum. Phosphorus occurs as these bright red spots, aluminum occurs as the blue areas, and magnesium occurs as these greener areas. Now we can see there's some areas that are circled in these white hash marked lines, and those are regions showing obviously different textures and potentially different chemical compositions, at least based on the elements picked in this map, as well as different shapes of particles. This is a volcanic spherule. And then in these inset electron images, we're actually seeing fragments of different rock types. So in the previous examples, we had an ideal case where we're measuring the minerals and their compositions from homogeneous rocks. We infer that the image or map that we've created is representative of the entire rock sample, which is commonly true of some types of igneous rocks. In this case, we can't make that same inference. So things like the volumetric abundance of minerals kind of fly out the window in an example like this. One of the challenges that's inherent in what I mentioned in that is we have to make assumptions based on examining our specimens to say that the slice of rock that we use to make the analytical specimen is representative of the rock, and we have to be able to determine that that rock is indeed homogeneous. Now, there's some pretty large assumptions made in addition to that, because our samples sometimes are the size of golf balls, sometimes they're the size of your fist, but we're not seeing a whole cliffside outcrop like we can observe here on Earth. So we do have to assume that these samples represent a homogeneous fragment of a rock under study. The other assumption that we have to make that's a limitation is based on the choice of elements that are used to create these maps. Are we choosing the right suite of elements that really represent all the mineral samples, all the minerals that we see forming the rock? And are we choosing the right suite of elements to catch these minerals? So the image on the right is what I think is representative of one of these opportunities. This is a test image that's a composite from an instrument that I failed to mention from one of the earlier slides. It's an instrument that currently occurs on the Mars 2020 rover called the Pixel. It's Another way that we can measure and create X-ray maps of samples using instrumentation. And in this case, PIXL stands for Planetary X-ray Instrument for Lithochemistry. This is, we use a technique called X-ray fluorescence, where we bombard the sample with high energy X-rays, which in turn cause the sample to give off characteristic X-rays, in this instance in the form of visible light that correlates to certain types of elements. And that's what we're seeing in this image here on the right. This is, again, a composite test image, but this time of a much more complicated rock sample. This is a mixed rock assemblage, and the image is trying to show what types of information we might be able to discern from looking at an image like this. And the idea is that the PIXL instrument will be collecting numerous types of these images that tell us about the rock types present on the surface of Mars in areas that are not composed of volcanic rocks. The challenge is, of course, these rocks are heterogeneous, and that we're going to see eventually rocks that we don't recognize based on the chemical compositions. So there will be interpretations based on elemental signatures, such as what we see here. Chert is a very high silica rock, and we see it being the principal cement in this other rock type that's known as a conglomerate. So there's about to be an abundance of different types of maps available for study. But what I think is an opportunity, especially using the volcanic samples from Mars, is to calibrate our deep learning techniques as they apply to X-ray images and X-ray maps to better understand how to pick out specific minerals, how to make determinations based on the occurrence of those minerals, their shapes and abundances, how rocks are texturally different. I think it's easily possible to teach the system to recognize the modal abundance of minerals based on pixel brightness values. And there's another technique called crystal size distribution analysis that allows us to understand how crystals grow based on the area and the shapes of crystals that could be adapted for this type of AI type of technique. Finally, Ping had asked that I mention about super resolution microscopy and how it pertains to the potential for this type of an analysis. And from my understanding of today's reading is that we can improve the resolution of low resolution images to a much greater degree so that we could create larger area maps, thus improving the opportunities for the aforementioned types of measurements and inferences. At this point, I will say thank you for listening, and I'm really interested in the conversation that's about to follow because I know almost nothing about deep learning techniques. So thank you for your attention.
Thank you very much.